Okay, this problem involves a spring, so there's going to be a non-constant force, which means it has to be solved using the work energy technique. If you haven't already tried to solve this problem, I suggest you do so now before you watch the video. So let me draw a diagram of what's going on here. So we have this block of mass m that travels for a grand total of 2.45 meters. The last little bit of that mass is compressing spring, horizontal spring. Compresses that spring by 0.45 meters. The mass of the block, 15 kilograms. The spring constant is 280. And the coefficient of kinetic friction is 0.33. Alright, so let's look at the forces on the mass m. So there's going to be gravity, of course, and the normal force, and there's going to be kinetic friction, and then eventually also the spring force. The spring force doesn't act on it right away, but it will act on it once it gets over to the spring. The displacement vector, the motion, delta S, points in that direction. We'll use our standard Cartesian sign convention since the motion is to the right. Alright, so that does it for the free body diagram. I think I've got everything included on there. Let's go ahead and start doing the work energy theorem technique and see where that leads us. Again, if you haven't done this problem, you should pause the video and try to work on this before you watch the answer. So looking at my four forces, I've got the normal force, gravity, spring force, and kinetic friction. Okay, so the work done by the normal force, of course, is 0 because it's perpendicular to the motion. Same thing for gravity. The work done by the spring force, that always takes on the form 1/2 kx squared because it's minus the change in the spring's potential energy. And in this case, it's negative because the spring opposes the motion. If you really want to get technical about it, I can go up here and show you that this is minus the final minus initial, right? And the final potential energy of the spring when the spring is compressed is 1/2 kx squared. The initial potential energy of the spring is 0 when the spring is relaxed, so that gives you minus 1/2 kx squared. That works out to be minus 28.35 joules, given K of 280 and X of 0.45. Work done by kinetic friction is going to be the force of kinetic friction times the displacement times cosine 180, right? Because kinetic friction points to the left and displacement points to the right. So turning that cosine 180 into a minus sign, I get minus 0.33 times the normal force times the total displacement, which is 2.45, right? We're using 2.45, not 2, and not 0.45, because this entire surface that the mass moves on is rough, all the way down to the spring, so we've got to include the complete displacement. Now the normal force in this problem, if I sum all my y forces, the normal force is just equal to gravity. Okay, so that's just 147 newtons. There's no other vertical forces in the problem. So this works out to be minus 118.85 joules. Okay, so the work energy theorem tells me that the sum of the works by all the forces is equal to the change in kinetic energy. The final kinetic energy is 0 because the spring reaches a maximum compression of 0.45. This is like a max height problem, right? The mass temporarily stops when the spring reaches maximum compression. And then here's our V naught at the beginning of the problem that we're looking for. So when I add up all the numbers here, I get minus 147.2. Both the works here are negative. You have negative 28.35 and negative 118.85. They both slow the mass down. That's equal to minus 1/2 times 15 times V naught squared. And so when I solve for V naught, I get 4.4.